This is 5.2. Our objectives for today are the student will be able to use properties of rational exponents to simplify expressions with rational exponents, and use properties of radicals to simplify and write radical expressions in simplest form. Now today we're going to do a lot of work with the textbook because there's a lot of examples there and the notes are rather large, so instead of writing them out, we'll just look at it in here. And so the first thing we're going to look at is properties of rational exponents. And so these are things that you did in Algebra 1. But our core concept would be the properties of rational exponents, where A and B are real numbers and M and N are rational numbers. So remember, rational numbers is something that can be written as a fraction. And so here's the properties that we're going to deal with. The first one is the product of powers. And the product of powers says if you're going to multiply two things that have the same base, so these are both base A and base A, then the exponents you add, so a to the m plus n. So an example would be, since these are both base 5, we add the exponents, so 1/2 plus 3/2 would be 4/2 or 2, and then 5 squared can be simplified to 25. And then a power of a power is when we have a base, and then it's in parentheses with the power is to another power. And when you do that, you multiply the exponents, so m times n. So an example here is 3 to the 5/2 power to the second power. Then we take 5/2 times 2. Now you can do 10/2 and reduce to 5, or you can do the 2's cancel. And so either way you get 3 to the 5th, which is 243. Then the power of a product is when you have two things multiplied together and it's to a power outside, then you take the power and you go to each one of those. It affects each one. You can't do that when there's addition subtraction, only when they're multiplied, so when it's a product. So an example here would be 16 times 9 to the 1/2. That 1/2 power would affect the 16. We get 16 to the 1/2 and 9 to the 1/2. Now remember, 1/2 power, if I did that as a radical, it would be the square root of 16 times the square root of 9, and the square root of 16 is 4, and the square root of 9 is 3, and so 4 times 3 is 12. When you have negative exponents, okay, remember a negative exponent sends it opposite where it's located. So if it's a to the negative m, it would be 1 over a to the m. So it just moves it to the denominator, and then the power becomes positive. So example here is 36 to the negative 1/2. So you move 36 to the denominator, it becomes a positive 1/2. So again, that would be the square root of 36, which is 6, and it's in the bottom, so we get 1/6. If you had something where it was a negative power in the denominator, then it would move it opposite, and it would become 2 to the third power, because it would move the 2 to the top. The zero exponent, remember, anything to the 0 power is 1. And the reason for that is, well, we'll get to that next. When you take the quotient of powers, a to the m divided by a to the n, with multiply we add, so with division we subtract the powers. So here's an example, 4 to the 5/2 divided by 4 to the 1/2. You subtract 5/2 minus 1/2 would be 4/2 or 2. And 4 squared is 16. Which takes us back to why the 0 power is 1, because if I had x to the third divided by x to the third, and we subtracted, 3 minus 3 would be x to the 0, and we all know that anything divided by itself is 1. So 213 to the 0 power is 1. And then the last thing is the power of a quotient. We get a over b to the m. Then that power affects both the numerator and the denominator. So you get a to the m over b to the m. Again, it's as long as b is not equal to 0. Anytime you have a variable in the denominator, they have that on several of these. Should have brought it up earlier. Anytime your denominator is in the, or your variable is in the denominator, you can't divide by 0, so you can never have that as equal to 0. So this distributes to both of them. So this says 27 over 64 to the 1/3 power. So you do 27 to the 1/3. So that's the cube root of 27, which is 3. and then that would be the cube root of 64, which is 4. So again, you can do it this way and do it in your head, or you can again type it into the calculator just using that. So these are the rules that we're going to use on this assignment to simplify exponents. And so if we look at the examples, this is multiplication, so we add the exponents. 1/4 plus 1/2. Remember, when you add fractions, you have to get a common denominator. So I'm going to change this 1/2 into fourths. And you have to multiply 2 by 2 to get to fourths, so you multiply the top by 2. So 1/4 plus 2/4 is 3/4. Here, we have it multiplied and the power outside, so remember that power now multiplies to both of those. Again, we can only do if it's multiplication. So it becomes 6 to the 1/2 times 2, and 4 to the 1/3 to the second. And so again, a power to a power we multiply. So 1/2 times 2 is 1, so we get 6 to the first. 1/3 times 2 is 2/3, so we get 4 to the 2/3. And since you can only combine them if the bases are the same, so we just leave it that way. So it just becomes 6 and then times 4 to the 2/3 power. And they just want to choose, you could also, if I wanted to write this in radical form, it would be 6 times the cube root of 4 squared. That's if I didn't write it with fractional exponents, but you can just leave it in this form. The next one, again, they're multiplied. We have a negative power, so remember you want to start in parentheses. And so what they did here was they took, and since these are both to the 5th power, they rewrote this. And they put the 4 and the 3 together because they're both to the 5th power. So it's the same thing. They did that so they could simplify this. And so then we take a power, and they multiplied the 4 times 3 and changed it to 12 fifths. And then again, it's still to the negative 1/5. And then a couple ways you can do this. You can move this to the denominator and make it positive, but they just went ahead and multiplied first, which is what I would do. Power to a power you multiply, so 5 times negative 1/5 becomes 12 to the negative first. And then because it's a negative power, it moved it to the denominator, and you put a 1 on top, so it becomes 1/12. So on this one, 5 over 5 to the 1/3. Remember, if you're dividing, you subtract powers. If there is no power, remember it's always to the first. So they wrote it as 5 to the first over 5 to the 1/3. And then we subtract, so 1 minus 1/3 is 2/3, so 5 to the 2/3 power. And then lastly, on this one we have 42 to the 1/3 and 6 to the 1/3. So again, because these were both the same, they just rewrote it. So they put the 42 over 6 to the 1/3 and still have the 2 outside. Then they reduce this. 42 divided by 6 is 7. And then a power to a power you multiply, so 1/3 times 2 is 2/3. Excuse me. So we get 7 to the 2/3. So go ahead, and now I'd like you to try the monitoring progress. So try 1, 2, 3, and 4, and then pause this, go back, try it, and then come back and see how you did. So on this, power to a power we multiply, so you should have gone 2, and then added 3/4 plus 1/2. Again, we have to have a common denominator, so I'm going to change that to fourths, and we get 3/4 plus 2/4 is 5/4. So you should have gotten 2 to the 5/4. This one, the base is the same, so that's 1, so we're doing 1 minus 1/4, so that would be 3, and then to the 3/4. This one, so here again, these 1/2s are the same, so we're going to regroup this and put 20 over 5 to the 1/2, and then we still have this to the 3rd power outside. So 20 divided by 5 is 4. And then a power to a power we multiply, and so that would be 4 to the 3/2. Now, I don't know if the book will leave it this way, because you could simplify this, because I can write 4, it's kind of nice to simplify these. I can write 4, if we go here I'm going to change the 4 to the 3 halves. I can rewrite 4 as 2 squared. And so now I would multiply this and go 2 times 3 halves would be, the 2's would cancel and I get 2 to the 3rd, which would equal 8. So actually this equals 8. Another way to do it would be to write it as the square root of 4 to the 3rd, and the square root of 4 we know is 2, and 2 to the 3rd is 8, and we're done. So I don't know if the book is going to leave it this way. If you have something like that, if you can simplify it further, you might have to get the right answer in the computer. And then the last one, so these aren't the same bases. So I'm going to go ahead and distribute the 3 to those. So we multiply. 1/3 times 3 is 1, so we get 5. And then 3 times 1/4 is 3/4. And so we just get 5 times 7 to the 3/4 power. So hopefully that worked out for you, and it makes sense now if it didn't. So next, our next thing we're going to look at, simplifying radical expressions. So the power of a product and the power of a quotient properties can be expressed using the radical notation where m equals 1 over n for some integer n greater than 1. So these are just some properties that we can look at. Remember, we talked about this before. The product property says we can now, we're doing the same thing except now we're doing it over square roots. So the nth root of a times b can be broken up into the nth root of a times the nth root of b. So as an example, we can use this both ways. We can go from here to here, or we can go from here to here. And that's what they did on this example problem, was when they went from here back to here. They went the cube root of 4 times the cube root of 2. They multiply this. If the index is the same in both, you can multiply those together. So 4 times 2 is 8, and then the cube root of 8 is 2. This next one says that we can take a index with a fraction and break it up into 2 parts. Remember, you don't ever want to leave a fraction inside there. So you can do this. Here's what they did. They rewrote it this way and then took 162 divided by 81. The thing to remember is, if these indexes are the same, you can just divide. You don't need to take the time to rewrite this. You can just say, oh, these are both 4th roots, so I can divide 162 by 2 and get 81, and I can go directly from here to there. And then the 4th root of 81 is 3. So, they've got some examples here for us. So if you look at this first one, it says the cube root of 12 times the cube root of 18. So I'm going to show you the way the book did it. I'm showing you other ways you can do these things. So they've broken into 12 times 18 because these are the same, so I can multiply that together. They went 12 times 18, and they got the cube root of 216, which is 6. And that's fine if you recognize that. Another thing you can do is simplify it. Well, I guess you can't simplify these, so that would be the only way to do that one. The next one, the 4th root of 80 divided by the 4th root of 5, because these are the same, we can just divide 80 divided by 5 is 16, and then the 4th root of 16 is 2. If you get stuck on being able to go from here to here or from here to here, remember you can go back and do 216 to the 1/3 power. And that will tell you if it's a perfect cube or not. Same thing here, I can do 16 to the 1/4 power. So, the next part, it's really important to understand this. An expression involving a radical with index n is in simplest form when these 3 conditions are met. So again, just like the core concepts, you're probably going to write that stuff down. No radicals have perfect nth powers as factors other than 1. Now it sounds confusing, it's just this. That I can't leave this as the square root of 50 if there's any perfect squares in that. So there's lots of ways you can do this. A lot of you in algebra class did it this way. You did the factor trees, and you said, oh, I can break that into 25 times 2, and then 5 and 5. And then remember, if you had pairs, the pair comes out front and is gone, and what I don't have pairs for stays inside. So that's one way to do it. Another way to do it is to do what's called the waterfall method and just go like this and take the smallest number that goes in. You know, 2 goes in 25 times, 5 goes in 5 times, 5 goes in once, and as soon as you get to 1 you're done, and then the same thing. You have a pair, so the pair comes out and then the square root goes inside. What I personally like to do, but because I know my square roots, is I know that this breaks into 25 times 2 right now. And so what I do is I write it above it and then say, oh, the square root of 25 is 5, so it comes out front, and I can't take the square root of 2, and whatever I can't take the square root of stays inside. So it's just whatever works best for you. No radicals contain fractions. That means I can't leave something like the square root of 6 over 25. I can't leave it that way. I have to break it up into this. Okay? And then, but the problem with that is it goes against our last one that says no radicals appear in the denominator. So we can't leave this here. In this case, we can just, the square root of 25 is 5, and I can get rid of it that way. But, let's say I had the square root of 7 over the square root of 3. So now what you do, and we've done this earlier in the year, to get rid of the square root of 3, you multiply by the square root of 3 over the square root of 3. And so we get the square root of 21. The square root of 3 times the square root of 3 is the square root of 9, which is 3. Just remember, anytime you multiply a radical by itself, it's the number without the radical sign. So let's try some of these. So example number 3, it says write each expression in simplest form. So they want us to break the cube root of 135. So we have to be able to tell what numbers are there that go into 135 that I can take cube roots of. So if we just think about our cube root list we had 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216. So we're already past 135. So we just need to know if any of those numbers go in there. Well, even numbers can't go in there. So those are eliminated. We don't worry about 1, and 125 doesn't go into 135. So the only question is, does 27? And 27 times 5 is 135. So now what we do, again, and you can do this, you can still do the factor method on this. I'll show you that. 135. So that would be 5 times 27, 3 times 9, and 3 times 3. Since we're taking the cube root, it's the ones that you group them now in groups of 3. And so the same thing would be, it'd be 3 and then the cube root of 5. Make sure a lot of people will drop that when they come to do it. And so, if I break it down this way, I would just say the cube root of 27 is 3, and then that's gone, and then the 5 goes inside. So whatever works best for you. Now, this next one's a little more complicated, because these are fifth roots. So we have the fifth root of 8. So what you're looking for on this is numbers that go in, that 8 goes into, that you can take the fifth root of. So we know that 1 to the fifth power is 1. 2 times 2 times 2 times 2 times 2 is 8, 16, 32. Okay? So I can rewrite, or an easier way to write this, well, let's go this way. Since it's 32, what do I have to multiply 8 by to get to 32? So before, remember when we did the square root, you multiplied by the square root. If it was the square root, you'd multiply by square root of 8 over square root of 8. But now I want to get something I can take the fifth power of, which is 32. So this is 2 to the third. I have 3 2's here. I need something, 5 of them, so I need 2 more 2's. So I'm going to do the fifth root of 4. And the fifth root of 4. And so I get the fifth root of 28 over the fifth root of 32, which is 2. And I would be done. So let's see, yeah, book did the same exact thing. Okay, so they did the fifth root of 4. I just want you to understand where that came from. It's because I need, this is 2 to the third, and I have to have something that I have 5 of. So I need 2 more 2's, which is 4. So they did the same way. So, now we're going to get into a little more complicated. It says, for a denominator that is the sum or difference involving square roots, multiply both the numerator and denominator by the conjugate of the denominator, the expressions a square root of b plus c squared of d, and a squared of b minus c squared of d. So, let's just take, as an example, 1 over 2 plus the square root of 3. If I just multiplied by the square root of 3 over the square root of 3, I'd have to distribute that, and I'd get square root of 3, and then I'd get 2 square root of 3 plus 3. And I didn't get rid of that radical. I still have that radical in the denominator. But when you multiply conjugates, the conjugate of 2 plus the square root of 3 is 2 minus the square root of 3. So now when I multiply conjugates, look what happens. I get 1, distribute that, so I get 2 minus the square root of 3 on top. And in the denominator, I get 2 times 2, which is 4. I get a negative 2 square root of 3. And then I get a positive 2 square root of 3. So those are opposites and will cancel out every time to get rid of the radical. And then I get square root of 3 times negative square root of 3, which would be negative square root of 9, which is 3. So I get 2 minus the square root of 3 over 1, which is just 2 minus the square root of 3. So when we have a binomial, 2 terms down here with a square root or an imaginary number, we're going to have to multiply by the conjugate to get rid of it. So if we look at this first example, it says 1 over 5 plus the square root of 3. So I have to multiply by the conjugate, 5 minus the square root of 3. So, when we do this, remember this is what they're actually doing here when they multiply together, is they're doing this a squared minus b squared equals a plus b and a minus b. So we're doing the difference of 2 squares in reverse. Because the outer and inner terms will always cancel, I just have to square the first minus the second square. So, 1 times 5 is 5. 1 times negative square root of 3 is negative square root of 3. So we're going to so this 5 squared minus the square root of 3 squared. So you get 5 squared is 25. Minus the square root of 3 squared is minus 3. And so 25 minus 3 is 22. Let's look at a couple more examples. So, example number 5a. So remember, now we're doing addition, adding, subtracting. When you're adding, just like you do 5x plus 3x is 8x. If the variables are the same, you add the numbers in front. Same thing happens here. Since there's no number in front, it's considered to be a 1. 1 4 through to 10 plus 7 4 through to 10 is simply 8 4 through to 10. You just multiply the numbers in front and the radical stays the same. So because these are the same, okay, I just add the numbers in front, so I get 2 plus 10, so I get 12, 8 to the 1/5 power. Now you have to be careful here, because these are not the same. So when they're not the same, we can't add or subtract them, and else we can simplify them to get them where they are the same. So they took this 54, and they broke it down into 27 times 2. The cube root of 27 is 3. And then we have the cube root of 2. And then minus the cube root of 2. So now these are the same. So 3 minus 1 is 2 cube root of 2. So on a lot of these, you're going to have to simplify them first. So, would like you to try (5 through 12 here. So a lot of them we're going to try. We're going to make sure we understand this. So go ahead and try them. Come back and see how you did. So these are both the fourth roots. So we can multiply them together. 27 times 3 is 81. So we get the fourth root of 81, which is 3. These are both cube roots. So I can divide. 250 divided by 2 would be the cube root of 125. And the cube root of 125 is 5. The cube root of 104, now this is a little bit different. This isn't a perfect cube. So let's take and go ahead and break down that 104. So that would be 2 times 52, which is 2 times 26, which is 2 times 13. So you can see here, we need 3 of them now, so we have 3 2's. And so this would be 2. And then the cube root of the number we didn't find matches 4, which would be 13. The fifth root of 3/4. So remember, we can't leave that there, so we break it up into the fifth root of 3 over the fifth root of 4. Now, again, that's 2 squared. So I have 2 2's. I need 5 of them, so I'm going to have to multiply. I need 3 more 2's, and so 2 times 2 times 2 is 8, so I go to the fifth root of 8. And so we get the fifth root of 24 over 2. Because remember, we're getting the fifth root of 32, which is 2. This one, so this is where we have to multiply by the conjugate, so I'm going to go 3 over 6 minus the square root of 2 times 6 plus the square root of 2 over 6 plus the square root of 2. Okay? So now we distribute that. We get 18 plus 3 square root of 2. And then remember, it's 6 times 6, which is 36. The outer and inner terms cancel. So minus the square root of 2 times the square root of 2 is 2. So we get 18 plus 3 square root of 2 over 34. You should always check to see if you can reduce that. If there's something like 3 goes into both these, but 3 doesn't go into 34, and 2 goes, so you can't reduce it, so you'd be done. Alright? They're both the fifth root of 12, so we just subtract. 7 minus 1 would be 6, and then the fifth root of 12. These are both 9 to the 2/3, so we can add the numbers in front. So it would be 12, and then 9 to the 2/3. And then this one, they're not the same, so we have to simplify this. So let's go ahead and break down that 40. 4 times 10, 2 times 2, 2 times 5. We have 3 2's, so it's 2. 2 to the third root of 5. Now they are the same, so 1 plus 2 would be 3, and then the cube root of 5, and you'd be done. Alright? Now, this next part, I'm not going to really worry about it too much on the test, but you'll need it for when you do the problems. And And so on this, it tells us the property of rational exponents. It says when n is odd. So if our index is odd, remember if it's odd, we can do, we don't have to worry about it being plus or minus, because we can always do a negative number when it's odd, and we can always do a positive number when it's odd. So like the cube root of negative 8 to the third. Well, that would just be negative 8. We have problems sometimes when it's a variable, not when it's, like on this would be, when it's like this, you could rewrite it and go 6 over third, but you can just divide this if it's divisible. And so that would be x squared. I don't need to worry about it if it's negative, because the negative takes care of itself. But where you run into problems is when n is even. And so when n is even, you're always going to take this and you're going to say the absolute value of x. Because we're going to, that negative sign would disappear when I did this, because if this was negative 3, let's say that was 8, well, negative 3 to the 8th power is going to give me a positive number. So we're going to put absolute value signs anytime we have this. So on this one, because we have 4, the fourth root of 3 to the 4th, we're going to say 3, but when it's 4, negative 3 to the 4th power, we're also going to say 3, because that, if I simplify this first, that negative sign would disappear and I just get 81. So you'll have to remember that as you go through and solve these. Check your indexes. If it's even and you had a variable inside or a number inside, you're going to always make it positive, because we're just going to do the absolute value. So let's take a look at examples of this. So the index is odd, so I don't need to worry about keeping track of that. I just sheeted the cube root of 64, which is 4. And then I'll show you, the book does it this way. They break that y to the 6th into y squared to the 3rd. And that's fine. If that helps you, by all means do it. But with powers, all you have to do is divide. So 6 divided by 3 is 2, so it's 4y squared. So you can break it up if you want, but if I know the cube root of 64 is 4, I don't need to break it into 4 cubed. If I know that this power is divisible by the index, then I can just go ahead and divide it. But sometimes it's not. And so let's take one where it's not. Let's say that was the cube root of 64 y to the 7th. Well, what I do is I break it down into something that is. So I can do the cube root of 64, so that's good. And then I just break this y to the 7th into y to the 6th times y. Okay? So now the cube root of 64 is 4, so that's gone. 6 divided by 3 is 2, so y squared, and that's gone. And then I can't do the cube root of y, so that I would leave that like that. So you can break it down into the same power as the index if you want, or you can just divide. So if we take this next one, so here's an example of where we have to do the absolute value. So this is they broke it up into 2 fractions. The 4th root x 4th, because this is even and it comes out odd. If it comes out even, like on this, we didn't need to worry about the absolute value because the square takes care of it. You only have to worry about it when the index is even and you end up with odd at the end. So because 4 divided by 4 is 1, it's x to the 1st, and so I have to put those absolute values in. Okay? I'm not going to worry about it so much on the test, but on the computer it's going to want you to put those in, so make sure that you do. Next example. So let me take you through the way the book does it, and then I'll show you the way I do it. You can do it whichever way is easier for you. So the book says the 5th root of this, 4, a to the 8th, b to the 14th, c to the 5th. So they just break it down into parts that they can do the square root of. So you can see here, they broke the a in, we need it to be 5 go in. So they broke it into 8 to the 5th times 8 to the 3rd. It's pretty much the same thing. B to the 10th times B to the 4th and C to the 5th. So they're doing it the same way I would. I would just put it up above here. So now, here's where they break it up into parts they can do the 5th root of and the parts they can't, which is fine. So they do, remember, you just divide. 5 divided by 5 is 1, so A to the 1st. 10 divided by 5 is 2, so B to the 2nd. 5 divided by 5 is C to the 1st. And then the parts you can't. So, it's fine. You can do it this way. Or from right here, you can just say, oh, 5 divided by 5 is 1, so I bring an A out front. Let me put it up above here. So I can do the A to the 5th, so that's gone. I can do the B to the 10th. 10 divided by 5 is B squared, so that's gone. I can't do B to the 4th, but I can do C to the 5th, and so that's C, so that's gone. And then whatever's left stays inside. 4, A to the 3rd, B to the 4th. Okay? So just two different ways of doing it. If you look at the next one, so on this one, again, different ways to do this. We need something we can take the cube root of. And so they took the cube root of y to the 8th, and so the first thing divisible by 3 that's greater than 8 is 9, so we need one more y. So we go 3y to the cube root of y, and so now when you multiply that, you would get the cube root of y to the 9th, which they have here, and then on top, x times the cube root of y, and then again you just divide. 9 divided by 3 is y to the 3rd, and you're done. Another way you could do that, some of you might, this is pretty easy this way, but you could reduce that to start with. You can break that into x, and I'm going to break that into the cube root of y to the 8th. I'm going to break that into y to the 6th times y squared. And so 6 divided by 3 is 2. And then the cube root of y squared. And then because I need one more y, because I have two of them, I multiply by the cube root of y over the cube root of y. And then y squared plus y would be y to the 3rd. And so you get a y there times the y squared would give us that y to the 3rd again. And you get the same answer. Just sometimes people like to break it up into smaller pieces. And then the last one, remember negative exponents. Send it opposite where it's located. So I would start on this. I would just simplify this. Let's see how the book did it. Okay, so yeah, we're just simplifying it. So you can see here, they did 14 divided by 2 is 7. And then they take the x's. Now remember, when you divide, you subtract powers. So 1 minus 3/4, which would be 1/4. Then they have 1/3. There is no y's in the bottom, so that stays 1/3 y. And then the z to the 6th, you just move it opposite. So that's one way to write it. I would, if I'm doing this, I just know that negative power I'm going to move to the top. So that would become 14xy to the 1/3 z to the 6th. And then I would reduce. 2 goes into 14 7 times. And then 1 minus 3/4 is x to the 1/4. Whichever way seems to make sense to you. You do it the way the book does, where they break it up and do that, or you can just cancel and work that way. So, let's take a look at example number 8. So on this, again, we're just adding and subtracting here. They're both the same, so we add 11 square root of y. On this one, they're not the same. We have to break this up. So we're doing cubed. I can break 54 into 27 times 2. I can't do the z squared. So we get 12. There's I can break this 2z to the 5th into z to the 3rd times z squared. So 3 divided by 3 is 1, so I get z. And then inside I keep the, I still have that 2 there, so I have a 2z squared. On this one, I get minus, the cube root of 27 is 3, so I get minus 3z. I can't do the 2z squared, so the cube root of 2z squared. And so now, since these are the same, I can subtract 12 minus 3 is 9z. And then we get the cube root of 2z squared. And we're done. Okay? So, I'd like you to try 13, 14, 15, and 16. And then come back and see if you did it correctly. So on this one's kind of nice. The cube root of 27, I can do 27, and 9 is divisible by 3, so I can do that. So the cube root of 27 is 3, it comes out front. 9 divided by 3 is 3, so q to the 3rd. There's nothing left inside, so I'm done. On this one, again, you could break this up, but you really don't need to because they're both divisible by 5. So 10 divided by 5 is 2, so x squared. And 5 divided by 5 is 1, so we get y. Let's take this next one. 6 divided by 3 is 2, so that's gone. I took care of that. We have x to the 1st and x to the 1/2, so we subtract 1 minus 1/2 is x to the 1/2. And 3/4 minus 1/2, I'm going to have to change that to 2/4. 3/4 minus 2/4 is 1/4. And so you should have gotten 2x to the 1/2 and y to the 1/4. Lastly, we're taking the square root of this. So again, I can take the square root of 9. 5 is not divisible by 2, so I'm going to break that into w to the 4th times w. So the square root of 9 is 3. 4 divided by 2 is w squared, and then we get the square root of w. On this one, I can break that into w squared times w. The square root of w is w. So now remember, I have to multiply it by what's out front, so w times w is w squared. And then that's gone. And then I get the square root of w. And then because now these are both the square root of w, I can add what's in front, so 3w squared minus w squared is 2w squared. And the radical stays the same. And you're done. So these, believe me, some of them get kind of complicated. So you have to take it really slow, make sure you have it. So next is the problems. So the assignment is page 248, numbers 3 to 69, the odds. I'm going to give you 2 classes, so we're going to be able to work on this in the class period we gave it, and then the next class period you're going to have time to work on it again. So it's going to take 2 days to do this. So do your best, really look at it, try and break it down. Make sure when you do it that everything's really clear as you go through and do it so you don't make any mistakes, because it's easy to make mistakes on it. So hopefully this helps. If not, we'll look at examples in class and hopefully take care of it.